afternoon, everyone. I am Harshad SS, an electrical engineering intern at Abhyaz. I am here to deliver a webinar on the topic Single Stage Inverters in Power Electronics. So, in this webinar, I will start with a brief introduction about inverters and the problems associated with conventional inverters. Then, I will discuss about the single stage inverters which can overcome the drawbacks of the conventional inverters. I will also discuss about the Z source and quasi Z source inverters. Am I audible? Can anyone respond to that?
Yes, Harshad, audible.
Yeah, okay, fine. So, okay, fine. So, in this webinar, I will start with a brief introduction about the inverters and the problems associated with the conventional inverters. Then I will discuss about the single stage inverters which can overcome the drawbacks of the conventional inverters. I will also discuss about the Z source and quasi Z source single stage inverters followed by the split source inverter. At last, I will compare the requirements and performance of all the three inverters. Let's start with inverters. Inverter is an electrical device which converts DC power into AC power by sequentially turning on and turning off electrical switches. They changes the magnitude and frequency of the DC input. Inverters find its application in renewable energy system, uninterruptible power supply, electrical vehicles, consumer electronics, and grid tie systems. The inverters used nowadays are conventional inverters, which consist of a DC input, switches, and a load. There are some drawbacks associated with the conventional inverters. In conventional inverters, the output voltage can never be higher than the input voltage. If we want a higher output voltage, we need to introduce a boost circuit which increases the size and cost of the inverter as well as reduces the efficiency. This is the block diagram representation of a conventional inverter for obtaining a higher output voltage.
Harshad, your screen is not visible.
Is it visible now, ma'am?
Yes, now it's visible.
Can I start from first again?
Yes, after inverter you can start.
This is the block diagram representation of the conventional inverters for obtaining a higher output voltage. As we need two electrical circuits to achieve the desired result, that is a boost circuit and an inverter circuit, we call it as a two-stage inverter. To address the limitation of the conventional voltage source inverters, we look into single-stage inverters. Single-stage inverters are inverters which combine both boosting as well as inversion operation by introducing an impedance network between the source and the converter. They can be more useful in renewable energy systems, motor drives, and UPS. In single-stage inverters, the boosting as well as the inversion operation are performed by a single circuit. There are many single-stage inverters developed recently, but for today, I will explain about three such inverters. They are Z-source inverters, quasi-Z-source inverters, and split-source inverters. Now let us understand more about Z-source and quasi-Z-source inverters. In that, first I will explain about Z-source inverters. It has the ability to temporarily boost the input voltage to a higher level. This is achieved by inserting a unique impedance network consisting of inductors and capacitors. The impedance source networks offers short circuit protection during shoot-through conditions. In the circuit diagram of Z-source inverters, we could observe the impedance circuit inserted between the bridge circuit and the supply. Since it resembles alphabet Z, it is known as a Z-source inverter. For designing the network components, I have used formulas mentioned below. That is, for designing the inductors and capacitors of the Z-source inverter. Now let us have a look into the operation of the Z-source inverter. It has two operating states known as shoot-through state and non-shoot-through state. In shoot-through state, the impedance network is short-circuited to achieve the boost operation. During this state, the energy gets stored in the impedance network and dissipated during the non-shoot-through state. Here, we have the circuit diagram of Z-source inverter during the shoot-through operation. Shoot-through is nothing but turning on switches belonging to the same leg simultaneously. In non-shoot-through state, the circuit operates similar to that of a conventional voltage source inverter. Here, the input diode gets turned on, which connects the supply with load. The DC input voltage as well as the inductors transfers energy to the load. PWM, that is pulse width modulation, is a technique employed in the output stage of inverter to recreate the AC waveforms by switching the DC voltages on and off with higher frequencies. I am implementing a simple boost PWM for Z-source inverters. It can be also used for quasi Z-source inverters as well. In this simple boost PWM, the reference signal is a sinusoidal wave and the carrier signal is a triangular wave with a higher frequency. In addition to that, there is a DC signal which is used to perform the shoot-through operation. Whenever the magnitude of the sine wave is greater than the magnitude of the triangular wave, a pulse is generated. The complement of the signal is provided to the switches of the same leg. Also, whenever the magnitude of the DC signal is lesser than the carrier signal, all switches are turned on to enable the shoot-through state. To overcome the limitations of the Z-source inverters, such as high voltage tests across the inductors and capacitors and lower system reliability, we look forward into quasi Z-source inverter. It is a modified version of Z-source inverters which retains the key features of the Z-source inverters. In the circuit diagram, Harsha, shall I continue?
Yes.
Okay. To overcome the limitations of the circuit diagram of quasi Z-source inverters, we observe that the structure of the network has been altered to overcome the disadvantage of the Z-source inverter. These are the design equations which I have used for designing the network parameters. Here also, we have a shoot-through state and non-shoot-through state mode of operation, which is very similar to a Z-source inverter. During the shoot-through state, the diode is in off position and the capacitors transfers energy to the inductors. In the non-shoot-through state, again, which is similar to the normal state operation observed in a conventional voltage source inverter. Some disadvantages of the impedance source networks include utilization of the complex control algorithm and increased number of components. To overcome these problems and to obtain a better performance, a single-phase split-source inverters were designed. A single-phase split-source inverters provide a single-stage conversion. As the name infers, the DC source is split up from the DC link such that both the inductor and the capacitor are charged and discharged to accomplish the inversion and boosting operation in a single stage. It has two common cathode dual configuration to link the boosting inductor to H bridge. This configuration helps in reducing the parasitic inductance in the commutation path of the diodes. These are the switching states in the inverter, namely active state 10, active state 01, 0 state 11 and 0 state 00. During the active state, the inverter operates similar to that of a conventional VSI. In 0 state, either the switches from the upper legs or lower legs gets turned on simultaneously. The L charges when at least one of the switches from the upper leg gets turned on and discharges when both the switches in the lower leg gets turned on. These are the design equations for the for implementing the split source inverter. One advantage of SSI is that even simple sine pulse width modulation technique can be implemented to operate this inverter. For reducing the oscillating charging and discharging duty cycle of the network elements, a combination of constant and varying reference wave is needed. In this pulse width modulation technique, I have used inverted sine wave and a constant wave as a reference wave, and triangular wave as a carrier wave. Whenever amplitude of the sine wave is greater than amplitude of the carrier wave, a pulse is generated. I have also used two reference waves, red one for the switches S1 and S2 and blue one for the switches S3 and S4. Now let us compare the performance and requirements of the three inverters. We could observe that the number of inductors and capacitors has been reduced in split source inverters, and also the voltage gain of the split source inverters is higher than the Z source inverter and quasi Z source inverters with reduced total harmonic distortion. I have also implemented Z source inverter, quasi Z source inverter, and split source inverter in MATLAB Simulink. This is the Simulink circuit for Z source inverter with a DC input voltage, a diode, two inductors, two capacitors, a H-bridge circuit, a filter circuit, and a load. For operating this inverter, I have used a simple boost pulse width modulation technique. In the simple boost pulse width modulation technique, I have used a sine wave as a reference wave and triangular wave as a carrier wave. Now let me explain how the switching operations are occurring for switches S1 alone. So first, when a sine wave is compared to a triangular wave, a set of pulses is generated. Later, I am comparing a triangular wave with a DC signal and producing another set of pulses. So I am making an OR operation between the first set of pulses and second set of pulses to generate a pulse for switching operations of switch S1. We can observe the output in the scope window. Here we can see that this is the output generator by comparing a sine wave and a triangular wave, and this is the output generator by comparing a sine wave and a triangular wave and a DC signal. So this is the result of OR operation between the first wave and the second wave. By performing this pulse width modulation technique, we could observe sinusoidal output at the voltage. This sinusoidal output has occurred because of using the filter circuit. If I have not included the filter circuit, then you could observe a quasi-sinusoidal waveform. I have used the same modulation technique for the quasi-Z source inverter also, but here there's a small change in the structure of the network. So I have used the same modulation technique here also, and I have observed the output through scope window. So we could observe that in quasi-Z source inverters, the time taken for settling at a constant output voltage, it's basically faster than a Z source inverter. The time taken is less for a quasi-Z source inverter. So similarly, I have also designed a split source inverter. For this split source inverter, I have used quite a complex pulse width modulation technique. So in this technique, I have used a sine wave as a reference wave and a triangular wave as a carrier wave. So here I have for half a time period, I am providing a sine wave as a reference wave, and for second half of time period, I am providing a constant wave as a reference wave. So these two reference waves are switched using a switch here and multiplied with 0.8 because I have chosen a modulation index as 0.8. So after performing this operation, we could observe the output here. So here we have the carrier signal as a triangular wave and the inverter sine signal and a constant signal as a reference wave. For observing this output, I have reduced the frequency, but initially I have given the frequency as 10,000 Hz for better operations. By increasing the frequency, we could also reduce the losses of the circuit. So after changing the frequency, I can run this simulation. So I've given a stop time as 1 second. So this simulation will run for 1 second. So this is the output voltage waveform for the split source inverters. Let us observe that this voltage settles at 80 volts. So in summary, I will conclude that SSI provides better efficiency, higher voltage gain, and high performance when compared to other inverters. In futures, solar panels can also be incorporated with split source inverters along with MPPT algorithms to maximize the output. So I could conclude with a quote that an inverter is like a bridge connecting the world of direct current to the realm of alternating current, empowering us to harness electrical energy efficiency. I would like to thank Abhyaz for providing me with this opportunity, and I also like to thank the participants who are patiently hearing this webinar. Thank you very much, and if you have any questions, please post in the question and answer